In this presentation, we consider Archimedes' work Quadrature of the Parabola. In this, Archimedes wrote a letter to his friend Dositheus that was motivated by their mutual friend's passing, that mutual friend being Conon. It turns out that all three of them had been interested in geometry, and so Archimedes talked about how there were previous attempts to compute the areas of certain conic sections, but those previous results relied on lemmas whose truth was not known, since the proofs didn't exist. And so it was very interesting that Archimedes was able to give two proofs of the following results. That being, every segment enclosed by a straight line in a section of a right angled is a third again of a triangle having the same base as it and an equal height. In other words, Archimedes was able to compute the area of a certain conic section. Now, in order to understand and analyze the actual statement of this theorem, we consider a few definitions that Archimedes gave that preceded Proposition 18 in this letter. His definitions state, I call base the straight line of segments enclosed by a straight line and a curved line, and height the largest perpendicular drawn from the curved line to the base of the segment, and vertex the point from which the largest perpendicular is drawn. In other words, given a curved line or a parabola BCA, we're going to draw a line BA that then truncates that parabola, and thus we're given a certain parabolic segment BCA. In this, BA is going to be called the base. Now, if we let BA denotes or the base give the x-axis, then the height is essentially the largest y-coordinates of all the points that lie on the boundary of this parabola, and then the vertex corresponds to the points with the largest y value. Now, Proposition 18 also gives a few equivalent definitions. The first one readily aids our intuition, that being, if we let BA denote the x-axis, then the vertex will be the points at which the derivative of the parabola is equal to 0. In other words, when the slope is equal to 0, or when the tangent at C is parallel to BA. So this conforms nicely with our intuition, but the Proposition 18 actually explicitly shows that given a parabola, a parabolic segment BCA, then if we bisect the line segment BA at the point M, and through M draw the line that is parallel to the axis of the parabola, then where this line intersects the parabolic segment, that will be in fact the vertex of the parabolic segment. This third recharacterization of what a vertex is will be very useful to us, namely since it will allow us to actually construct the vertex given a certain parabolic segment. And we note that because C is the vertex, then the triangles that we're going to be considering in a minute are just these triangles where the base is BA and the height is C. Then going into what the main theorem states again and analyzing it, every segment enclosed by a straight line in a section of a right angled is a third again of a triangle having the same base as it and equal height. In other words, given a parabolic segment, then 4/3 of the triangle that has the same base as the segment and has the same height as the segment then actually is equal to the parabolic segment. In other words, given a parabolic segment, then we construct a triangle with this base, and then we construct the opposite vertex to actually be the vertex of the parabolic segment. Then if we multiply the area of this triangle by 4/3, we get the area of the parabolic segment. And this is a very interesting result, as had been previously discussed in Archimedes' introduction to his letter. But now, how did Archimedes go about actually structuring his letter to get to this result? Well, he began with his preface to Dositheus, but then he immediately began by giving 5 propositions, which were just general facts about parabolic segments. Interestingly, we're just going to comment that 1 to 3 were not proved, but rather citations to proofs were given to conic elements. Now, propositions 1 through 5 can be found throughout the rest of the work. For example, 1 and 2, or it can be readily interpreted as such. So 1 and 2 can be given as a converse to 18. 3 is explicitly cited in 19, 5 is next cited in 14, and so these propositions do have value to the rest of his work. Then propositions 6 through 17 actually give a proof of the quadrature of a parabola by using center mass arguments. In particular, propositions 6 through 13 give lemmas about weighing the certain triangles and trapezoids, and then using those lemmas, propositions 14 and 15 actually approximate the parabola with triangles and trapezoids, from which propositions 16 and 17 give a proof of the quadrature of the parabola. Now, interestingly, after proposition 17, Archimedes then gives some definitions. These definitions were previously used, for those being what we covered previously. In other words, he defined what the base of a parabolic segment is and the height and vertex of it as well. It's interesting that he didn't cite or define these earlier because they had been used earlier. So we're going to impose a certain we're going to interpret this a certain way. Specifically, we're going to say that, well, Archimedes liked the arguments following proposition 17. In other words, he liked how propositions 18 and 14 gave a proof of the quadrature with geometry, so maybe that was his preferred method of proof. So we're just going to consider his geometry argument here. Actually, we're just considering it because it's also the material that's used builds off material that we have previously talked in this semester. So to give an idea of how Archimedes geometrically proved his quadrature of the parabola, suppose that we're given this parabolic segment, and let us describe the triangle that he talks about in the statement of his theorem. In other words, let this blue triangle have the same base and the height as the parabolic segment. Then we note that this parabolic segment can be readily described in three component parts, that being the blue area and then those two sub-parabolic segments. So if we would like to describe the area of the parabolic segment in terms of triangles, then it would seem reasonable to draw the same kinds of triangles in each of those two remaining parabolic segments, which then gives us 4 remaining parabolic segments. We can then continue this process repetitively, and it seems clear, at least with the picture anyways, that if we continue this process indefinitely, we will eventually be able to precisely describe the area of the parabolic segment by all of these triangles that have been successively defined iteratively from the previous steps. So assuming that we can, in fact, the sum of all of these triangles does in fact give the area of the parabolic segment, which does happen to be true, then if we wanted to be more explicit and compute the area, then we would form this sum. In other words, we sum up all the blue areas, the red areas, yellow areas, etc. Now, what's interesting is that the yellow areas are equal to one another, the red areas are all equal to one another, and the blue area, of course, is equal to itself. Thus, we can drop the subscripts. And moreover, there is one blue area, there are 2 red areas, 4 yellow areas, and it's clear that at each iteration there are twice as many triangles as the one before. In other words, we are justified in getting rid of the summation notation and then just multiplying them by this exponential factor with base 2. Now the real crux of Archimedes' argument was his observation that the yellow areas are an eighth that of the red areas, that the red areas are an eighth that of the blue areas. Of course, this can be similarly defined with the further iterations. In other words, they're just a certain 1/8 power of the original blue area. And so the area of the parabolic segment is given by the first infinite sum, that being the sum from n equals 0 to infinity of 2 to the n times 1/8 to the nth power multiplied by the blue area x. Interestingly, that sum can be rewritten as the blue area x multiplied by a certain geometric series, and that geometric series is known to converge to the value of 4/3. Thus, the area of the parabolic segment is 4/3 of the blue area. Now, we might ask, well, how did Archimedes actually go about proving this? And we'll consider that now explicitly. So proposition 18 recharacterized the height, which in turn, so given a parabolic segment, proposition 18 allows us to geometrically find the vertex of the parabolic segment. Then proposition 20 shows that the inscribed triangles that we consider are each comprise more than half of their corresponding parabolic segment. This explicitly this concretes our intuition that that all of the triangles do fill up the entire area of the parabola. Then Proposition 19 acts as a lemma for Proposition 21, where Proposition 21 states that each child subtriangle is an eighth of its parent. So what I mean by this is, referencing the previous slide, the yellow area is an eighth that of the red area, and the red area is an eighth that of the blue area, and so on and so forth, so that we actually can relate each of the triangles that we form to the original triangle for the original parabolic segment. Then because of the previous relations, we are naturally led to consider a certain geometric sum. So Proposition 23 then considers a truncated form of that geometric series. And since for arguments such as like Zeno's paradox, certainly Archimedes wouldn't want to extend the geometric sum out to infinity, so instead he considers a truncated form and gives an appropriate error term that does approach zero. And then finally approach zero as we increase enough terms. And then Proposition 24 gives a proof of the quadrature by an exhaustion argument. Now, we note that Proposition 22 was not listed in the previous bullet points because of the way that we now consider areas in our modern context. So Proposition 22 states that if we can associate each triangle with a certain square that has the same area as that triangle, then the question becomes, well, if we sum up the area of all those squares, does that ever exceed the square that corresponds to the area of the original parabolic segment? The answer is obviously no, because each of the triangles is inscribed within the parabolic segment. So Proposition 22 really just gives a formal argument saying that that is the case. And so we don't consider that to be a major part of Archimedes' geometrical argument. And then finally, we note that Proposition 24, what we mean by an exhaustion argument is that he shows that the geometric series considered in Proposition 23, that geometric series doesn't exceed the value of 4/3, and moreover, it doesn't fall below it as well. So in other words, it converges to the expected value. This is mainly because the error term approaches zero. Thus, this basically gives Archimedes' geometric argument that he gave in his letter to Dositheus. Now, most of these topics we have already discussed in some detail, so we already talked about the recharacterization of height. From the pictures, it seemed clear that the inscribed triangles would eventually fill up the entire area. Moreover, we explicitly described the geometric series that would give the area of the parabolic segment and so forth. The main idea that we haven't yet analyzed thoroughly stems from Proposition 21 that states that each child subtriangle is an eighth that of its parent. And we finish off this presentation by considering a proof of that statement to give an idea as to why that's the case. So suppose that we're given a parabolic segment ACB, where in order to compute the vertex, we then bisect AB at the midpoint M, and through M we draw the line that is parallel to the axis of the parabola, and then we consider the corresponding intersection with the parabolic segment. We label that C, and thus form the desired triangle ACB. Now, the claim will have been shown if we show that the angle that's the desired triangle that's inscribed in this parabolic segment over here, the parabolic segment AC, if that triangle's area is an eighth that of the triangle ACB. So in order to compute, or at least draw this triangle in this subparabolic segment, it would seem to make sense to bisect the line segment AC and then draw the same kind of parallel line. However, instead, we're actually going to bisect the line segment AM at the point P, and through P, we're going to draw the same parallel line. The reason for this is that actually we end up bisecting the line segment naturally anyway. So this triangle AWP is similar to the triangle ACM because these two angles A are the same, and clearly AWP and ACM are equal to one another because the line PW is parallel to the line MC. Moreover, since the line segment AP is half that of the line segment AM, then our observation of similar triangles leads us to deduce that the line segment AW is half that of the line segment AC. In other words, W does in fact give the bisected point of the line segment AC, so that our indirect construction is valid, and thus we get the desired triangle ADC that we want to show as an eighth that of ACB. we'll see that actually drawing this line down is being parallel to this line segment over here will be useful, and moreover, the nice feature is that P being half that of the line segment AM will be very useful to us later. That's why we did this indirect construction. Now, in order to begin showing that the areas satisfy that 1/8 relation to one another, we're going to certainly want to use the fact that ADCB is in fact a parabola. So in order to do that, we're going to draw the line segment DE that is parallel to AB. The reason for this is that we note that AM is half of the chord AB, so that AM is an ordinate of the parabola. And since all parallel chords, or all the midpoints of parallel chords, form a diameter of the parabola, then since DE is parallel to the line segment AB, where DE is then hits that diameter MC at E, we conclude that DE is itself an ordinate. Thus, there exists a constant fixed parameter P such that P times EC is equal to DE squared, and then P times MC is equal to AM squared. This just gives the main symptom, or states the main symptom of a parabola. Now, P itself isn't of much interest to us, lowercase p, so we're just going to take the factor, or divide out the factor by taking EC over MC is equal to DE squared over AM squared. Now we note that AM is twice that of PM. This is because, nicely, P was chosen to be the midpoint of AM. Moreover, since we have drawn the parallelogram PDEM, we conclude that PM is equal to DE. Thus, AM is equal to twice of DE, and thus we can cancel terms to get EC over MC is equal to a quarter. We then multiply MC out to deduce that EC is a quarter of MC, so that ME is actually 3/4 of MC, and thus we get this equality over here. Then we multiply the 3/4 out to get MC is equal to 4/3 of ME, and since ME is equal to PD, because PDEM is a parallelogram, we thus have MC is equal to 4/3 PD, and that was the main result from that argument that we're interested in. Next, we recall that the triangle AWP is similar to the triangle ACM, namely with AP being half that of AM. Thus, the side PW is in fact equal to 1/2 the line segment MC, and since MC was previously computed to be 4/3 of PD, we just substitute that expression in down here, and then we get PW is 2/3 of PD. So since PW is 2/3, WD will be 1/3, and hence PW will be twice that of WD. And that concludes the main part of this argument. Penultimately, we want to draw these three strings of equalities about the areas of triangles, and we're going to consider them successively. So to begin, we claim that the triangle ACP is twice the area of triangle ACD. This is because if we consider AC to be their base, they certainly have the same base, where the area of a triangle is 1/2 base times height. So since PW is twice that of WD, we readily conclude that the height of ACP is actually twice that of the triangle ACD. Thus, we get, since we have the same base, but ACP has twice the height, then the triangle ACP has twice the area of triangle ACD. Next, for the next claim, we claim that triangle ACM has twice the area of triangle ACP. This is because triangle AM has twice the base of is twice the base of AP, and since both triangles share the same opposite vertex C, they certainly have the same height. Thus, ACM has twice the base but same height as triangle ACP, so then we get this equality. And similarly, triangle ACB has twice the base of triangle ACM, but they have the same height, so thus we get this last equality as well. Then composing everything together, we finally get that triangle ACB is 8 times the area of triangle ACD, which concludes our proof. as that was what we wanted to show. Thus, we have gone over all the major elements in Archimedes' geometric proof of the quadrature of the parabola, and hence we conclude our presentation. We give references and note that we used Henry Mendel's translation of Archimedes' letter in order to get an outline or understand an outline of how Archimedes really structured his ideas. And then we cite Gordon Swain and Thomas Dents for providing motivation to the proofs that were given in and ideas of proofs that were given in this presentation. And thank you.